All right, let's talk about building with AI. If you're treating it like just another software library, you are, and I mean this seriously, setting yourself up for failure. Today, we are going to strip away all the hype and get down to the fundamental first principles of AI engineering. The stuff that will help you build systems that actually work in the real world. Let's get into it. Just look at this for a second. On the left, you've got your classic predictable code. It does exactly the same thing every single time. But on the right, that's an AI model. It's probabilistic. You could even call it stochastic chaos. And you know, the single biggest mistake engineers are making right now is treating the thing on the right like the thing on the left.
So let me be crystal clear. If you think import OpenAI is going to behave just like import pandas, your application, when it hits production, is going to fail hard. They're just fundamentally different beasts. Right now, most developers are caught in what I like to call the syntax trap. You know what I mean? They're scrambling to memorize the latest API calls or chasing after whatever new model just dropped. But here's the truth. The tools, the libraries, they change weekly. The underlying physics of how these things work, that does not. This all means you have to make a major mental shift. To build AI that's actually reliable, you have to stop thinking like a software engineer just writing code, and you need to start thinking like a systems engineer. So today, we're going to cover the 3 core principles that'll help you make that switch. Okay, principle number 1. This is the big one. We have to understand the massive difference between something that's deterministic and something that is probabilistic. Traditional code, right? It's deterministic. If I write a function that adds 2 plus 2, I can run it 1,000,000 times, and I am going to get 4 1,000,000 times. If I don't, well, that's a bug. It's something that has to be fixed. It's predictable. It's safe. But AI is a whole different ballgame. Let's just ask a large language model a super simple question. Explain gravity in 1 sentence. Okay, we get an answer. Now, what do you think happens if we ask it again? And again. See? We get 3 different answers. Now, they're all pretty much correct, but they're not identical. This is exactly what we mean by probabilistic. The system is designed to have this kind of variability. It's a feature, not a bug.
So here's what that means for you, the engineer. Your role has totally shifted. You are no longer writing explicit step-by-step instructions. Nope. Instead, your job is to manage the risk that comes from this fuzzy, probabilistic nature. Your code doesn't dictate the output, it defines the guardrails for that output. And this leads to a pretty critical warning. Look, if your whole system falls apart just because the model decided to use a synonym, a word it didn't use yesterday, then you haven't built a real product. You've just built a house of cards, waiting for a slight breeze to knock it all over. Your system has to be built to handle this natural variation.
All right, so now we know AI is probabilistic. Let's look under the hood a little. To really manage that probability, you've got to embrace our second principle. What these models are doing is math, not magic. It's really just incredibly sophisticated pattern matching. We love to use human words, don't we? We say the model is reasoning or thinking, but if we're talking first principles, it's not doing either of those things. It is simply predicting the next most likely token. Think of it as a word or part of a word, based on a giant, mind-bogglingly complex probability map it's learned from the internet. It's just pattern matching with some very, very fancy math.
So why does this distinction matter so much? Well, because once you really get that it's all just math, these scary-sounding concepts like hallucinations suddenly become a lot less mysterious. People are always asking, is the model lying to me? The answer is no. The model isn't lying. It doesn't even have a concept of truth. What's happening is that it's just really, really confident about a mathematical pattern that just so happens to be factually wrong in our world. Your job isn't to trust the math, it's to build guardrails around it.
And that brings us perfectly to our third principle. And honestly, this might be the most critical one for building anything that's actually production ready. Evaluation is way more important than implementation.
In traditional coding, just getting your code to compile and run feels like a huge win. In AI engineering, that's table stakes. It's barely even the starting line. Getting an answer from the model is the easy part. The hard part, the part that is like 90% of the job, is knowing if that answer is any good.
And this slide, this right here, gets to the absolute heart of professional AI engineering. If you can't numerically score your AI's outputs using what we call an eval, or an evaluation system, then you're not engineering, you're just guessing. You're going on a feeling, and you absolutely cannot scale vibes to 1,000 enterprise users who are depending on your system to work.
So let's bring these 3 principles together for a second. This whole thing isn't about memorizing one specific tool or one library. It's about adopting a brand new mindset for this new era of engineering. It's about mastering the fundamental physics of how these systems actually behave.
Think about it. The libraries that everyone is using today, they'll probably be old news in 18 months. But these principles, managing probability instead of writing instructions, understanding that it's all about token prediction, not true reasoning, and building systems for rigorous automated evaluation, those are the constants. Those are the things that will last.
Master the physics of how these probabilistic systems work, and you can build anything. It doesn't matter what new model or framework gets released tomorrow. This right here is the key takeaway. So, I'll leave you with this question to really think about for your own projects. Now that you understand the probabilistic soul of AI, its mathematical core, and the absolute need for evaluation, what guardrails are you going to build first?